Hi everyone, we're the Permafrost thawing rate prediction group, and we'll be using machine learning to predict the rate of thawing of permafrost in the Northern Hemisphere. So what is permafrost? Permafrost is a permanently frozen layer on or under the surface of the earth. Gravel, sand, and soil are considered to be permafrost if they're joined together by ice and have been frozen for at least 2 years. They hold 2.5 times the amount of carbon already in the atmosphere, therefore regulating global temperatures. If permafrost thaws at an accelerated rate, the carbon stored will be released, creating a positive feedback loop. The greenhouse gases emitted will further contribute to global warming and thaw more permafrost as a result, increasing overall global temperatures. The thawing of permafrost can also lead to the collapse of roads, houses, and other infrastructure as soil shifts. Therefore, it is critical to preserve permafrost, especially in the Northern Hemisphere where it is prevalent.
Greenhouse gases are various chemical compounds that trap heat in the Earth's atmosphere. When greenhouse gases are created as a result of human activities, there is an increase in temperature of the Earth's surface. Carbon dioxide, methane, and nitrous oxide are greenhouse gases that play a significant role in global warming. Carbon dioxide is the most common greenhouse gas, making up about 65% of total emissions and is primarily released in energy production. Methane is more effective than carbon dioxide at trapping heat, despite making up only about 25% of all greenhouse gases. Methane and nitrous oxide are usually released as a result of agricultural practices. Although nitrous oxide is not as abundant as carbon dioxide or methane, scientists predict that its global warming potential is nearly 300 times stronger than carbon dioxide, and it is a strong ozone depleting substance. As global warming thaws permafrost, carbon stored in the permafrost is further released in the form of greenhouse gases, perpetuating the cycle of global warming.
Okay, so I think the person's not here, but our method is to basically predict the future greenhouse gas emissions of methane and carbon dioxide, and we're also planning to include nitrous oxide. And because these three gases are the gases with the most impact. And we're going to use a linear regression model because this seems to be the most accurate out of the models we've tested so far. And our goal is to find a correlation between the rate of increase of greenhouse gas emissions and thawing rate of permafrost. And we're going to use the greenhouse gas data to predict the future thawing rate.
So, in order to predict future greenhouse gas emissions, we needed historical and current data of emissions of gases like carbon dioxide and methane, which are the most prominent in the environment. So, if we take a look at the data pictured above, it can be seen that the annual million metric tons of methane being released into the environment has exponentially increased over time. For example, during 1970 to 1972, it can be noticed that around 6,000 million metric tons of methane had been released. Almost 50 years later, the number has increased by 30% to around 9,000 million metric tons of methane. By analyzing this data that we have collected, we built a model to identify patterns and trends to predict future greenhouse gas emissions for carbon dioxide and methane.
So, in developing our model to predict future greenhouse gas emissions, we considered several different approaches, including linear regression, polynomial regression, random forest, and decision tree regression. After evaluation, we collectively chose to use the standard linear regression model. This decision was based on our belief that the relationship between our selected features, years, and total emissions measured in billion metric tons would exhibit a predominantly linear trend over time. Once the model type was selected, we moved into the training phase. We used historical data spanning from 1940 to 2020. This period was chosen to capture a comprehensive view of greenhouse gas emission trends, and by focusing on these years, the model could establish a baseline trend and develop a linear relationship between the year and total emissions. Our trained model was then validated using data from 2020 to 2023. This validation step ensured that the model accurately captured recent trends and offered insight into its predictive power and limitations. Currently, the model achieves a mean squared error, or MSE, of 0.32. This metric represents the average square difference between predicted and observed values, and a lower mean squared error indicates better model performance. An MSE of 0.32 demonstrates a relatively low level of deviation, suggesting that our predictions align relatively well with real-world data. This model has now been extended to make predictions for future years from 2024 through 2070, as shown in the bottom graph. By establishing a linear relationship between the year and the billion metric tons of greenhouse gas emissions, our approach aims to project future levels of carbon dioxide and methane emissions. This is a preliminary stage to our end goal of establishing a correlation between greenhouse gases and permafrost, which will use the information from this model as one part of the data.
Okay, to improve our model, one of the first things we'll do is implement additional variables like economic growth data and other environmental factors such as temperature and land use. This way, we can provide the model with more context, leading to more accurate predictions. Another improvement would be to experiment with alternative models. For example, polynomial regression can capture more complex nonlinear trends in the data, while other methods like random forest or gradient boosting can combine multiple decision paths to increase accuracy. Next, we can focus on hyperparameter tuning to enhance model performance. This involves adjusting parameters like regularization to avoid overfitting, which means making sure our model generalizes well to new data rather than just fitting the training data set too closely. Cross-validation is a useful tool here as it helps in selecting the best settings by evaluating the model multiple times on different subsets of data. Finally, validating the model using diverse datasets is crucial. By refining our validation datasets, we can effectively ensure that our model isn't just overfitting to a particular dataset and instead provides robust, reliable predictions across different scenarios. Thank you. And then this is just our works cited.